Alright, so let's look at a differential equation, basic one that we've done before. And if you remember from section 6.1, we said when you wanted to actually solve this differential equation, we're going to separate the dx and dy. We're essentially multiplying the other side by dx. We're taking the integral and we snuck in a little 1 there that's multiplied by that dy. And that's how we got y equals 5x plus c. And things I want you to remember is that when you take an integral from a to b, f of x dx, they are being multiplied in a sense. You're looking at this as the heights of the rectangle. You're looking at these as the width of the rectangles, and you're multiplying a bunch of rectangles, heights and widths, and then summing them as a Riemann sum. That's what this integral symbol, in a sense, kind of tells us. So the only way that you can integrate is if you're multiplying by dx, and that's going to be important as we kind of move through separable differential functions. Differential functions, I guess, could also work. All right, so to check if they're separable, you want to see if the function of x's is multiplied by a function of y's. So that would be something like this. Or that they're divided. So I'm going to give you a list of functions that are separable. So x times y. That's separable because it's a function of x times a function of y. This is separable because they're divided. And the last one is also separable because they are a function of x multiplied by a function of y. Now, why do I know that these are separable? Because I could simply use algebraic process to get them separated. And because I'm multiplying by dx, it multiplies that whole thing. So they're separated. All my x's are on one side, my y's are on the other side. So I want to see what happens if I try to separate this. Well, I need to move the y to the other side. But I would want to get the dx to the right side, but I can't do that, at least not easily. The other thing you should notice, you're taking your y and adding dy to it, and that's going to be a major issue because remember, the dy's and the dx's have to multiply so you can integrate. So that is the reason why these will not work. So this one's actually even easier. It would take one step to move the y's to the other side. But again, this plus is the issue. And trying to get the dx to the right side, that's going to be a little bit of a pain to do. It's possible, but it's going to be a pain. So, we're going to look at problems that are separable. And the major word being separable. This is actually a separable differentiable function. And the reason I know that is if I rewrite this with a dy dx, which is what I'm a little bit more used to, and I get the dy dx on its own, you end up with this type of equation, which might not look separable, but I can factor out the x. And when I do that, I have now separated the x and y's by multiplication or division. So, we're going to look at some problems. Let's start with this guy. I think it's the first one we did. To separate, I multiplied by dx, and then I integrated. We snuck in a little 1 right here. And we said this would be y equals. And then the k, if you are confused, you can pull the k out front, because that's a constant. Constant comes down, and then we do x squared over 2, and then plus c. Number 2, example number 2 that we did. Separate, I will multiply by y. I would multiply by dx, and integrate. And when I try to integrate, I get y squared over 2. On the other side, I get x squared over 2, and then my plus c. I'm going to multiply by 2 on both sides. Let's multiply 2 all the way out. So if I do that, I would actually end up with x squared plus 2c. And then I want to take the square root of both sides, but when I do that, I'm going to need a plus or minus. So I get y is equal to plus or minus the square root of x squared plus 2c. And then you'll see later that we can do things like, if this is just a constant, I can replace 2c with a new constant letter called a. So I really could replace and have this as my final answer. In terms of the plus or minus, you'll figure out which one to use because they're going to give you an initial condition like this. let's say 1 equals 5. In that case, because the 5 is positive, then my y value has to be positive. If, let's take this back, I ended up saying, oh, never mind, I wanted it to be a negative 5. The y value is now negative, which means I would have to use the negative symbol. All right, moving on. This guy right here, let's move the y's out of the way. So I would divide by y. I would multiply by dx. I'm going to integrate. And when I do that, this side is ln of y equals x squared over 2 plus c. So what do we get? Let's see. We end up with needing to eliminate that ln. Get the absolute value of y is equal to e to the x squared over 2 plus c. That whole thing is the power. Just so you're very clear, that whole thing is a power. And then if you remember, I said, well, if you have a squared times a cubed, you told me that that was a to the 5th, which is summing the powers. So, the other way around, if I have a sum, whoopsie, that's supposed to be a 3. If I have a sum of powers, I can separate them as a product. And that's actually what we're going to do in our next step right here. I'm going to rewrite this as absolute value of y is equal to e to the x squared over 2 times e to the c. Then we said, oh, well, if I want to get rid of this absolute value symbol, I can use a plus or minus. And I'm just going to move the e to the c in front, multiplied by e to the x squared over 2. And then we said, well, this whole thing is a constant. So let's rewrite that as a constant, meaning I'm going to rewrite it as a big old a, e to the x squared over 2. And a replaced, I'm going to do it in a lighter color, this whole plus or minus e to the c. Okay? Then we went into some harder problems. This guy here, we have dy over 1 minus y equals 2xe to the x squared dx. And we integrated the right side first. We said u was equal to x squared. We got du dx is equal to 2x. And then we have that du over 2x is equal to dx. So on the right side, we ended up with the integral of 2x e to the u times du over 2x. Cancel. Then we end up with the integral of e to the u du, and we were able to get that pretty easily. And then last step on the right side, I wanted to substitute back in my u, which was x squared. All right. That plus c is a big plus c. It's not part of the power. Now on the left side, we ended up with 1 minus y on the bottom. And I said, well, that's kind of like having a 1 power of 1. So that's really an ln hiding in there where the u, or the inside, is 1 minus y. So we can do a substitution where we use v equals 1 minus y. That will work. I'm going to do it without using substitution because if you look at the inside, which is 1 minus y, the derivative of the inside is a constant, -1, which means I can do this without substitution. So we're going to reverse the chain rule. We're going to antiderivative the outside, which was where we got the ln from, leave the inside alone, divide by the derivative of the inside. So what actually becomes of this? Let's take this all the way down to this line. We get negative ln of 1 minus y. If you do the substitution, you'll get the same exact answer. All right, meaning right here, follow that substitution down, you'll still get the same exact answer. So I'm going to actually multiply the negative to the other side. I am going to take e to that whole power, and we get 1 minus y equals, and right now I'm actually going to separate it. I'm going to do e to the negative e x squared multiplied by e to the negative c power. To get rid of the absolute value, I'm going to need a plus or minus. When I do that, I'm going to bring the constant term forward and then multiply by the variable term. And then I'm going to replace this whole guy with an A. And then, to get my final answer, I'm going to actually add y to the other side and subtract by the a term. So, moving y to the right side, add y. And then subtracting the a term to the left side. It's ugly, but that is the solution. So, that is the function for which the differential equation comes from. Alright, example 3, very similar. I'm kind of using a lot of the same terms, and so what I wanted you to see is that not every single problem we do is going to be an ln, because so many are, people get very confused. So if I do something like this is 100% not an ln problem. The integral of 1 is y, the integral of the y is y squared over 2. We already know this guy's answer. If you remember, we did it in the problem before, so I'm going to steal that answer. And this one I'm actually not going to have you solve for y. It's a quadratic function. A quadratic relation. Therefore, to solve for y, you would have to use the quadratic formula. We're not going to go through that. Letter number 4. Separate. Okay. So, integrate. And I'm going to actually rewrite this as a power. Because the only power that's ln would be -1 power, and that's -2. So, again, we can, and I will do it with this one, we can do a substitution for 1 minus y. For the ln problem, I chose to do it without substitution. Just so you understand that you could have used substitution, I will use it for this one. And then negative du is equal to dy. So, let's come over here. We end up with, actually, let's go far over to the right side. Oopsie. Alright, there we go. So, we end up with the integral of u to the -2 dy is the same as negative du equals the integral of this, which we already know the answer, so I'm going to substitute that in. If you remember, we already got e to the x squared plus c. On the left side, this negative will come outside. We end up with this integral, add 1 to the power, divide by -1, which will cancel the negative in front, e to the x squared plus c. And the plus c is a big plus c, not a power. And so we get 1 over u is equal to e to the x squared plus c. U is the same thing as 1 minus y equals e to the x squared, plus c is big. And then we're going to simplify that, or sorry, not simplify it. We are going to solve for y. So how would I do that? So y is at the denominator, and so I'd essentially have to multiply both sides by that denominator. I get 1 equals e to the x squared plus c, whole thing multiplied by 1 minus y. I'm going to divide by this term. So I get 1 over e to the x squared plus c equals 1 minus y. And then I'm going to add y so that it's positive. So I'm going to add y to this side. So y plus 1 over e to the x squared plus c equals 1. And then I'm going to subtract by that ugly term. Because here's what you can't do. Alright, so that is actually the solution. I'm going to show you the major mistake that I usually get is that people feel like oh, well, I want to reciprocal that, so we do 1 minus y, and then they start doing this. And that does not work. You can reciprocal both sides completely, but you can't do term by term. All right, and yes, there were many other ways you could have solved for y on the left side of this screen. I just chose to show you that method, but you could have done a full reciprocal of both sides, which would be this right here, 1 minus y, and then 1 over e to the x squared plus c, whole thing being reciprocal, not like above where you did term by term. All right, I believe that was the last piece, and then there was one problem which I guess I'll do. So let's look at it. On the axis provided, sketch a slope field. So I know that when x is 0, the slope field is 0. I also know when y equals 1, the slope field is 0. Which, oh wow, that's not y equal to 1. Y equal to 1 would be here, going across this way. All right, and then the other values, I'll just substitute in. Negative 1 squared is 1, 1, negative 2. So I am going to make myself a nice little table because I really don't want to do this in my head. So I get negative 1, 0, 1, 3, 2, 1, 0. All right, so x squared, 3 minus 1 is 2. We don't have to worry about that. We don't have to worry about the other term, this one. All right. And so we get negative 1 squared is 1. 2 minus 1 is 1. And then 0, negative 1. So 1 squared. And then 3 minus 1 is 2. 2 minus 1 is 1. And then the y, 0. So that's negative 1. In terms of what it looks like, 2, 1, negative 1, negative 1, 1, 2. All right, so that's part A. Part B, while the slope field in part A is drawn only at 12 points, it is defined at every point. Describe all the points where the slopes are positive. So if I want the slopes to be positive, this is part B. The only way I could get them to be positive is if this piece is positive. The x squared doesn't do anything. I need my y minus 1 to be positive, and the only way that could happen is if y is greater than 1. Other ways that I could have done that, I could have easily made a sign chart for y. 1 would make it 0. If I put in 0, it would be negative, and then positive. Therefore, this would be the solution I'm looking for, which is y greater than 1. The other thing I want to add in is that x also cannot be 0, because if x is 0, then you would end up getting a 0 as a slope, and they're asking for only positives. Part C, particular solution. I'm going to actually go over to the next page, and it was f of 0 equals 3. The differential equation is x squared y minus 1. And I'm going to solve the differential equation. So dy over y minus 1 is equal to x squared times dx. We're going to integrate. We're going to integrate. On the left side, you end up having the integral of y minus 1 to the negative 1 power. On the right side, you have the integral of x squared dx. On the left side, it should tell you that that's an ln problem. If you're having some trouble with this, use a u, and this is the reason it's ln, because it's negative 1 power. So I'll do the u substitution right here. U is equal to y minus 1. Du dy is equal to 1. Du is equal to dy. And so I end up with the integral of u to the negative 1, dy is the same as du, is equal to x cubed over 3 plus c. The left side would be ln of u equals x squared cubed over 3 plus c. And then, in this case, ln of the absolute value of y minus 1. All right. So, now, I want to use e. There we go. Cancel. I end up with the absolute value of y minus 1 is equal to e to the x cubed over 3 times e to the c. To get rid of the absolute value symbol, I use a plus or minus. I'm going to put the constant in front. I'm going to replace this whole thing with an a. And I end up with y is equal to a e to the x cubed over 3 plus 1. Now, very close to the final answer, except for I need to use the initial value. And I'm going to try to squeeze that right here. So let me see if I can kind of draw a nice little box. So the initial value was f of 0 equals 3. So I'm going to substitute 0 and 3. So 3 is equal to a e to the 0 over 3. So that's 0, and then plus 1. That's 1. So a is equal to 2. Therefore, my final equation would be y is equal to 2e to the x cubed over 3 plus 1. All right? The plus or minus is taken care of because the a value ends up being positive 2. All right, and then there was one last place I kind of added in. I wanted to add in the second derivative. So, the second derivative, so dy dx is equal to x squared times y minus 1. So that would be a product rule to do my second derivative equals leave the first one, derivative of the second, plus leave the second one, derivative of the first, let's see, 2x, and then substitute in. We get x squared times y minus 1 plus y minus 1 times 2x. Let's take out the greatest common factor, which would be x times y minus 1. So we get x cubed plus 2. And that would be the second derivative. There you go. So that's pretty much everything you would have to do for 6.4 day 1.